Remember I said, I just want them to know if they're actually listening to this, that we're going to push our test back on Tuesday. We'll review all these limits and stuff, and then we'll review again on Wednesday, and then we'll test on Thursday. Okay. Um, we're going to go ahead and do 2.5. It is the last section, and then um, go from there. So you will have homework, but I think this is a short section. I don't think it's very long. All right, so consider the function f of x equals 3 over x minus 2. Is that you? Gosh.
I'm hungry, but I'm trying not to be loud.
Well, there's nothing you can do about that, so you might as well just go ahead and eat.
You're so good.
From the figure and the table, you can see, and we'll do the table in just a minute, and I didn't put the figure on there, but you guys can check that out. It's at the very beginning of 2.5. You can see that f of x decreases without bound. Guys. As x approaches 2 from the left. So let me put this in your calculator, show you what it looks like. So from 2 to the left, it's pointing down. So that's that without bound that it's talking about. So I just wanted you to see, this is the graph, this is the figure that's in your book, okay? And f of x increases without bound. Sorry, I squished that up. As x approaches 2 from the right. So I'm going to show you one more time that graph. 2 from the left, you're going to come from the left side of your calculator and follow the graph. When you get to negative 2, you can see that it's pointing all the way down, going to negative infinity. This one is going up to positive infinity. That's what you're doing today. That's literally it, okay? So when you fill in your chart and we look at our table, we'll have 1.5 changes to negative 6, or it gives us a value of negative 6. Then it's negative 30. Negative 300, negative 3,000. That's a question mark, you can't see. We're looking for what happens at 2. And then on the other side, it just does the positive in the opposite direction. 3,300, 30, and 6. So again, from the table, you guys, the table does the same thing the graph does. From the left, you can see that the values are getting substantially larger. So you know it's going to negative infinity. From the right, they're getting larger. So it's going to positive infinity. All right. So the behavior is denoted as the limit as x approaches 2 from the left. And I'm not going to rewrite that function, but if you want to, you can. Do that all the time. Is negative infinity. And the limit as x approaches 2 from the right of that function is positive infinity. The symbols infinity and negative infinity refer to a positive and negative infinity. These symbols do not represent real numbers. They are convenient symbols used to describe unbounded condition more concisely. A limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. All right. Let f be a function that is defined at every real number in some open interval containing c except possibly at c itself. The limit as x approaches c of f of x equals infinity. Means that for each m greater than 0, there exists a delta greater than 0, such that f of x is greater than m whenever 0 is less than x minus c less than delta. All of that is that formal definition of a limit. Okay, remember I told you we don't really like that or use it, so we'll come back. So similarly, the statement, the limit as x approaches c of f of x equals negative infinity, means that for each n less than 0, there consists a delta greater than 0 such that f of x is less than n whenever 0 is less than x minus c in absolute values less than delta. So the same exact thing. So the only difference in these two are that m is positive and n is negative. Same thing here. It would be greater than or less than. That's the only thing different. To define the infinite limit from the right, replace 0 less than x minus c less than delta. By c minus delta is less than x less than c. The next one is the same thing. Sorry, this one's the left. I apologize, y'all. So if you're writing in pen, I super apologize. You can just write the other one if you want to. The next one is the right. So it's the same thing, infinite limit from the right, except for it's going to be c less than x less than c plus that delta. So infinite limit from the right. I apologize. All right. Be sure you see that the equal sign in the statement, f of x, the limit of f of x, equals infinity, does not mean the limit exists. On the contrary, it tells you that the limit fails to exist by denoting the unbounded behavior. I'm going to write this underneath so you guys can see it. Unbounded as x approaches c. All right, so remember we talked about limits that didn't exist or ones that were unbounded. That's what it's saying, but we can make them exist by doing left to right. Okay, so, and I told you that too. So defining infinite limits from a graph, determine the limit of each function shown as x approaches 1 from the left and 1 from the right. So the limit as x approaches 1 from the left of this function right here. We're just going to look at the left side. Where is it going? To positive infinity. One from the right is the other side. Where is it going? There you go. What about just the limit as x approaches 1? Very good. It does not exist because it's unbounded. Look at your next one. The limit as x approaches 1 from the left of this f of x. So from the left is this side. Where is it going? Positive infinity. The limit as x approaches 1 from the right. So as we trace from the right, it goes down to, what about the limit as it approaches just 1? Good. All right, any questions on this? Also, we talked about removable and non-removable discontinuities. Both of these have non-removable because you can't get rid of the vertical asymptote. Okay, so on these, there's nothing I can do to factor it out and make it look any different. It's going to look the same every single time. Okay, if you can factor it and you mark it out, so we talked about a hole, that's a removable. Okay, so if you're confused about removable versus non-removable, that's where it's at. And so we'll go over that too. All right, so vertical asymptotes. If it were possible to extend the graphs from the last example towards positive and negative infinity, you would see that each graph becomes really close to the vertical line. X equals 1. This line is a vertical asymptote. Of the graph of f. So that definition, if f of x approaches infinity, or negative infinity, as x approaches c, from the right or left, then x equals c is a vertical asymptote. And again, you can write all the words out if you know what it's going to stand for later. A professor in college that wrote symbols, I didn't know what they were. I dropped that class real quick. Couldn't even read my notes, didn't know what the symbols meant. Is everybody good? All right, in the first example, note that each of the functions is a quotient and that the vertical asymptote occurs at the number. So the first function is a quotient because they're being divided. And that the vertical asymptote occurs at a number at which the denominator is 0 and the numerator is not 0. The next theorem generalizes this observation. It's long. It's going to take us forever. It's not. Oh. Y'all ready for the weekend?
Yes.
Me too. Me too. All right. Theorem 214, vertical asymptotes. Let f and g be continuous on an open interval containing c. If f of c does not equal 0, g of c does not equal 0, and there exists an open interval containing c such that g of x does not equal 0 for all x excluding c in the interval, then the graph of the function h of x equals f of x over g of x. So it's saying, again, if you plug in c, you don't want to get 0. G of c on the bottom cannot equal 0. Then you have a vertical asymptote at x equals c. Y'all, you've been doing vertical asymptotes since math 3 at least. At least since math 3. So when we have rationals, so look at B, we did rationals in math 3. We factored the top, we factored the bottom if it was possible, and we marked out what we could. When we marked out holes. When we leave something in the denominator, that's what causes the vertical asymptote. So there's nothing we can do to fix A. So the way we find our vertical asymptote is we take that denominator and set it equal to 0. You do not have to show all of this work. I can pick out vertical asymptotes just by looking at the denominator, okay? Just like if you factored and solved. So this, I know that 2 is not going to do anything. So we would divide by 2 to solve this. It's not going to do anything. Then we get x plus 1 equals 0. And we would subtract 1 over and get x equals -1. That's where your vertical asymptote is. Can you see that just by looking at this factor? Yes, you don't have to do all this work, okay? So then let's look at B. Let's look at B. Can I factor the top? No, because it's plus, I can't factor the top, so it's good to go. On the bottom, sorry, my paper moved. I can factor it into x plus 1 and x minus 1, right? How many vertical asymptotes are you going to have? 2. Where are they at? That's it. That's all it's telling you. All that crap above it is just telling you how to find your vertical asymptote. You will have one if you can't get rid of it. That's what it's saying. All right, so what about this? What about this? What is cotan? What? Okay, we're not doing triangles. What is cotan? We're not doing triangles. It's the opposite of tangent, right? So 1 over 10 is what it is. So this is 1 over 10. It's okay. It's okay. It's 1 over 10. And guys, you know that 10 looks like the little S's, right? Lots of vertical asymptotes in that. Does everybody understand that? There's lots. So these are the harder ones to do because you got to think about how can I get each one of those. So then tangent, remember, is sine over cosine. I don't divide fractions, I flip and multiply. So it's actually going to be sine x over cosine x. I'm sorry. I literally just said flip it, and I didn't flip it. Cosine x over sine x. Cosine x over sine x. You're going to set your denominator equal to 0, and I'm going to do it up here because I'm running out of room. Denominator equal to 0. You guys see all these vertical asymptotes? So where sine x is equal to 0, I'm gonna show you on this calculator, is everywhere it touches. Now, the problem is I have this in like 1, 2, 3, 4. Sine, cosine, and tangent are always in terms of pi, right? Okay, so I'm gonna change my table set. I'm gonna start at 0. I'm gonna change my table to pi. Let's do, oh, I don't care about that. Hold on, window, this one. Negative pi, pi, and let's go pi over 2. It doesn't matter. Y'all can put whatever you want in there, but I'm just making it in terms of pi. So this little mark is pi over 2. This mark is pi. This is negative pi. So when is it equal to 0? 1 pi, 2 pi, 3 pi, 4 pi. Does everybody understand that? So we can't just write it like that because we've got to make sure that we write every single one of them. So it would be n pi, every integer times pi. Those are the ones that are kind of weird. All right. There's my big gap for the work. Sorry that I did that, left that gap. Theorem 2.14 requires that the value of the numerator at x equals c be non-zero. When both the numerator and denominator are 0 at x equals c, remember that's the indeterminate form. Indeterminate form. And you cannot determine the limit. That's the reason it's called indeterminate. Behavior at x equals c without further investigation is illustrated in the following example. And again, I didn't need to leave that much space. I guess I was too lazy to go back and look at it and fix it. So that space is not needed. All right, determine all the vertical asymptotes of the graph of f of x equals x squared plus 2x minus 8 and x squared minus 4 over x squared minus 4. All right, so what do I do to figure this out? Factor it. On the top, factors of negative 8 that add to positive 2. Negative 2, positive 4. That's okay. On the bottom, how do I factor x squared minus 4? X minus 2, x plus 2. All right, so you got some of these last night. And it said tell if they're removable or non-removable. We can cancel out this x minus 2, right? That is a removable. That's what makes it removable. Points of discontinuity that you can mark out. So it's still going to be a point of discontinuity because it's a hole, right? But we removed it from being that weird vertical asymptote.
Which will make the continuity negative?
No, you still have it there.
Wait, even if it is removable?
Yes, you still have it. Very good. All right. So then we're only left with this x plus 2 on the bottom. So where is my vertical asymptote? At x equals negative 2. All right. Again, if you graph it, x squared plus 2x minus 8. Nope. Hold on, it's still on the pi over 2. I should have zoomed 6. Here's why it's still there. You can see the vertical asymptote at negative 2, right? When we look in our table, zero, 1. What happened at 2? Sorry. Second table. There it is. So it's still there. So it's still going to kill your domain, but it's not a vertical asymptote. So you removed that vertical asymptote is basically what you're doing. All right. Determining infinite limits. So again, let me throw this out here. You removed this point from being a vertical asymptote. That's what makes it removable versus not removable. All right, look at your next example. Find each limit. And again, it's setting it bound from left to right, not just one. So what do I have to do first for this? What should I try to do first? Factor. If you can see that it's not going to do anything, like this one is not going to do anything, then you don't necessarily have to factor, but I would do it just in case. All right. So what do you notice? So that means something happens at that 1, right? That means your limit's probably not going to exist because you have a vertical asymptote. So then we're going to put it in so that you guys can see it. X minus 3, X minus 1. Graph it. We're looking at the limit from which side? The left. So here's the left side. What's happening? So the limit is positive infinity. What about from the right? We're not doing it, but we're about to. What happens from the right? When you trace it, it drops down to negative infinity. So this one, that's the only thing it did is it changed it to the right. It's going to be negative infinity. This spacing on these notes are all jacked up, and I am so sorry. All right, let C and L be real numbers and let F and G be functions. Good job. Here's your 1, 2, and 3. We're almost done. It's pretty quick. Your 1 is your sum and difference. We've already talked about that before. Sum or difference. So the limit is x approaches C of f of x plus g of x will still equal infinity. Your product, the limit as x approaches C. There's going to be 2 of these. The first one, so I'm going to go ahead and write this again so you know. We're going to do 2 in the product of f of x times g of x will be infinity, but only when the limit is greater than 0. Same thing for the next one, but negative infinity when the limit is less than 0. You're going to see examples of these in just a second. I'm so sorry, y'all. And then the last one is the quotient, where the limit as x approaches C of g of x over f of x will be 0. Does it smell like cookies? Do y'all think it smells like cookies? I think it smells like something baking. Like the cafeteria is baking cookies for today. All right. Last thing, 4 examples, and then we're done. Find each limit. So we just talked about the sum or difference. Try to pop all that up there at the same time. It says the limit of x approaches 0 of 1 plus 1 over x squared. You can take the limits as x approaches 0, I'm sorry, of 1. And you can also take the limit as x approaches 0 of 1 over x squared. Remember, this is direct, so anytime it's there already a number, and this one is going to be 1. This one what happens is x approaches 0. Doesn't matter which side you're looking at. What happens? What is it? Positive what? Infinity. So that means that the limit as x approaches 0 of 1 plus 1 over x squared is going to be infinity. Sorry, y'all. I'm going to do part D. It's the same exact thing. You can have the limit as x approaches 0 from the left of x squared. We're going to look at the limit as x approaches 0 from the left of 1 over x. From the left, you're just going to start with your calculator to your left right here. What happens is I get to 0. This is an actual point. So what is your limit? You could have also done this by direct substitution. If I do 1 over x, as I approach 0 from the left, goes to negative infinity. So what is this limit? Negative infinity. Not for this one. You would have to graph it because it's going to have that vertical asymptote. So if it's at 0, the limit will not exist. But if we bound it, it will be. Okay. All right. B. B is dealing with the quotient property, obviously, because I have a quotient. So if you find the limit as x approaches 1 from the left of x squared plus 1, you guys should already know that this can be direct. Why can this be direct? Say it again. It doesn't give you that indeterminate form. It doesn't have the 0 on the bottom or give you the 0 over 0. So it's a continuous graph. That's why. So I'm actually going to have a point. So as I go to 1, if you need to look at your table, what is your coordinate? 1 what? 2. So your limit is 2. The limit as x approaches positive 1 from the left of cotan pi x. What was cotan? 1 over tan pi x. 1 is over here. I'm approaching from the left. So what happened? Where does it go? Negative infinity. So then what is the full limit? That's it. I lied to you. I was looking at the bottom one. How about you? Property 3 says what? If the limits exist, what happens? It goes to 0. And let me see if I can show you that through this. Alpha y equals x squared plus 1 over, nope, don't do it that way. 10 x. Sorry. Tangent graphs always take 20 years to graph. I apologize. Right here. 0 from the left. What's it at? 0. Does everybody see that?
Show me a line. I need it here.
Hold on, I'm still graphing. Let's do -2. It's going to take 20 years to graph, but you're going to be able to see it. There's your -1. What happens at 0? 0. So for this one, I would not use the property. The only way I would use the property is if there's a vertical asymptote, and in this one, there's not, wherever we're bound at. Does that make sense? Graphing them, I think graphing them, finding the limits are the easiest way to do it. This would be if you had to do it by hand, you would need to know the properties.
So I want it to be -1.
Because from the left, as we approach 0, what is that coordinate?
I thought we were approaching
Oh, same thing. Here's 1. Sorry. Same thing. If we were approaching 2, what would it be? Same thing. Is everybody good? If we had come from the other side, same thing. Sorry, y'all. I kept looking at this one, that's why. All right, see, limit of 3 times ln x. This is that property 2. So this one, just in case you forget where I got that from, property 3. This is that property 1. Property 1 at the top of your paper. This one is the product. So we're going to do the limit of 3 as x approaches 0 to the right. And we're going to find the limit of ln x as x approaches 0 from the right. What's this one going to be? Without doing any work. 3. What about this one? We're going to put it in our calculator because I don't know how it works. I'm going to graph it. What's it doing? I'll zoom 6 for you if you need it. What's it look like? What's it look like? What are you thinking it is? Don't just sit here and talk. What do you think it is?
1.
We're approaching 0 from the right, so it's definitely not 1. It looks like it's -2, right? It's really not. It's really not. So remember, let's see. What can we put in if it's for 0? What do we have? What were those values that we had? Right. So it was like -0.1, then -0.001, right? But we're coming from the right, so we need to go the other way. So what were those? 0.1, 0.01, 0.001, 0.001, 0.00001. What's happening? Did it stop at 2? Where's it going? everybody see that? So be careful. Sometimes your graph will limit you to that. So watch those LNXs. We know that those are weird ones. So this one actually goes to negative infinity. So then by the property, even up here, the product property says f of x times g of x is going to be positive infinity if the limit is greater than 0, and then if the limit is less than 0. So this one is going to be, it's going to be negative infinity because that limit is less than 0. No, you can go off the graph. That's what I told you. I would never do it by the properties. I would never. Okay. They're just showing you these properties, and can you graph it by hand? Can you graph this by hand? So when you get the calculator inactive part, what are you going to do? You probably going to skip it. It's what you're going to do. But when you do this, if you can't, I'm being honest, if you don't know the properties, you see what I'm saying? Yeah. So for now, let's just work our calculator, and when we get more comfortable with limits, then we can start talking about non-calculator, okay? So I want you to understand the concept before I throw too much crap at you. So yes, right now, watch your graphs. But here's what the biggest thing was, watch this LNX right here. So you guys thought it was the 2 or whatever it was, and it's not. Is everybody good? All right. It looks bad. It's not. Okay. So, oh, sorry. 2 through 58 even. It's quick. If you're going to graph them, it's going to be quick. You're so whiny. I'm just saying. Yep. All right. Grab yourself a sheet of paper. Remember, I'm still recording. All right, let's look at this real fast. Again, get out a sheet of paper. I'm about to do some homework with you. Let's go. All right, number 2. It says in the exercise 1 through 4, determine whether f of x approaches infinity or negative infinity as x approaches -2 from the left and the right. So all you're going to write, the limit as x approaches -2 from the left of f of x. You guys know how to write that. The limit as x approaches -2 from the left. And just put f of x. Don't put the function. Don't write more than you have to, okay? Equals. From the left, where does this graph go? That's part A. Rewrite the same thing, but we're going to the right. So the limit as x approaches -2, the plus sign, f of x. As we approach from the right, where does it go? Ta-da, you're done with question 1, 2, whatever it is. Right. Same thing on the next one. You're going to write the same exact thing. The limit as x approaches -2 from the left, we're going to start on the left, of f of x equals we're only looking at -2. So from the left, from the right, there's question 4. Let's keep going. All right, look at number 6. It says, as it approaches 4 from the left and the right. So on number 6, I'm going to put this in my calculator. -1 over x minus 4. And I'm going to graph it. We're looking at as it approaches 4. What happens at 4? What do we have at 4? How about that? Vertical asymptote. So from the left, what does it do? Positive from the left. Negative. First 3 problems. From the left, it goes to positive. From the right, it goes to negative. Oh my God. From the left, it's the positive. From the right. I keep it consistent, always do left to right. That's how I read. I don't know if you read like that, but that's how I read. You might, you never know. All right, the next one, the only difference is that I have squared on the bottom. So when I graph it, it's gonna look like this. Where did both of them go? Ta-da. When I told you this was quick, I was serious. Like it really is. The longest it takes you forever to put it in your calculator. Are you okay with 10 and 12, or you just have to fill in the chart? They give you the chart. Okay. So on 10, 2.1, 2.2, whatever. Okay, I'm gonna show you. I'm gonna show you. All right, so to put it in your calculator, put your function in, guys, please. X squared over x squared minus 9. And then your table set, we're going to change to ask. Table set, you change to ask. So you understand that? Table set is right here, second. And then once you get it there, when you go back to your table, it's whatever you put in. So -3.5, you're just writing the values down. And if you guys don't want to make the table and you just want to write just that bottom value of lines, that is perfectly fine. Don't stress out about it. -3.1, -3.01, -3.001. We'll see what happens at -3. Obviously an error because it's a vertical asymptote. -2.999, -2.99, -2.9, and -2.5. Yeah. So what does it do? And basically the only ones you need to look at are the ones right at -3. So from the left, this is from the left, right, in our chart. Where do you think it's going to? If it's 1500. Positive infinity. From the right would be coming back this way. It's a -1500. So where's it going? Negative infinity. That's it. What it is. So 12 is the same way. Just watch how you put that in because it's cotan. Okay, so just watch that. All right, let's look at 14. So you guys have 12 to do right now. Just 12. We're going to look at 14. 14 is just find the vertical asymptote. What's the vertical asymptote on 14? 3. You don't have to do any work. Does everybody understand? How'd you get 3? X equals 3. Yep. Then you can write VA, and I do the little at symbol, X equals 3. How'd you get that? Just switch the sign, right? So look at 16. Look at 16. What about that one? Oh, can you factor that? No, because it's plus. So if I had to solve it, what would happen? How would you solve x squared plus 9? It's not a good question. It's an easy question. Subtract 9 and then, can I square root a negative number? No vertical asymptote. Can you graph it? You can see that there's no vertical asymptote if you'll graph it. So if you get one that you're a little bit confused on and you're like, graph it, see if I have one.
This is gonna sound really dumb. Can you graph it? Rather now than on the test.
No, you're good.
None of us are good.
This happens.
The learning experience.
I know.
Here we go. Look at it. Look. It's like a sideways S thing. It's continuous. It has no vertical asymptote. Got it? All right. 18. How do I factor that bottom? Plus 4 minus 4. What are your vertical asymptotes? Ooh, that's 18. Yeah. Okay. That's what I say every time. Yesterday was easy. You're making it more complicated than what it is. We're going to talk about it.
Yesterday's homework makes more sense today.
Probably does. All right. What about 20? Be careful. Be careful. Yeah, there's 2 of them. All right, yeah. So let's look at 20 for just a minute. This is one, Haley, that you always mess up factoring. Not in a bad way. You've asked me about it a couple times. So on the top, I have x to the 3rd minus 8. Those are perfect cubes. So remember, I take the cube root. So my first factor is the first sign. Square the first. Change the sign. Multiply them together. X times 2 is 2x. Square the last. So plus 4. If you can factor them, you need to factor because what happened on this one? So is there a vertical asymptote? No. That's removable discontinuity. So cube root. And then that becomes your first factor, but you use whatever sign it is. So that's a minus. So x minus 2. Square the first. Square the first. Change the sign. Multiply them together. 2 times x is 2x. And then square the last.
So they cancel out.
If there is nothing left in the denominator, there is no vertical asymptote. Okay. All right. Is everybody good with that one? Yeah, so there is a discontinuity at 2. It is a removable discontinuity at 2, but it is not a vertical asymptote.
This makes homework yesterday.
What would be your domain for this? Or your, okay, I'd ask for your continuity. Describe the continuity. We don't include 2 to infinity. That was yesterday. Don't tell me you don't know how to do it. Yeah. Absolutely. 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 We're going to keep going. We're going to keep going. Yeah. We're going to keep going. All right. So 22. 22. Let me get my little sticky note back up here. 22. On the top, we know how to factor that one. That was an easy one, right? Remember what I told you about the bottom? Sometimes you might have to switch it around. This one you don't have to, but you want to try to factor it. And you do that by grouping. So x cubed plus 3x squared. This is the only way that you can factor 4 terms at this point. There are some of these that I can't factor, and I just look on the calculator for them. Okay, so don't stress out about it. So what's in common between these two? X squared leaves me with x plus 3. What's in common with this one? A -1, right? Leaves me with x plus 3. So my first factor is x plus 3. You guys see this second factor right here? What can I do to it? What is x squared minus 1? Can I factor it more? X plus 1 minus 1. So I just did it all at one time. All right. So here's your top. We'll rewrite it so you can see both of them. X plus 3x minus 3. On the bottom, and I'm going to move it up so you guys can see it. Right there. What do you notice? So that's a removable discontinuity at x equals -3. Nope, this is yesterday's homework. Yesterday. What I'm talking about right now with the removable discontinuity is yesterday's homework. Vertical asymptotes. -1 and positive. All we're looking for are vertical asymptotes, okay? That's it. But again, everything else I'm talking about is what we did yesterday. All right, so we're confused about e's. X e to the -2x. Does that have a vertical asymptote?
No.
So what do you do if you don't?
For these? The first thing you need to understand is e are exponential and they're continuous anyway. They're not going to have any vertical asymptotes.
So there's no vertical asymptote.
If there's no vertical asymptote, you're right, no vertical asymptote. But yes, this would, so last night's homework, what would your continuity be? Negative infinity, positive infinity. There's no breaks or gaps or anything.
I don't know if I'm going to be able to figure out if there's vertical asymptotes.
You factor.
No vertical.
This one is no vertical asymptote. And that's why, what if you don't have a calculator? You should know that e's are exponential and they're always continuous, increasing, decreasing. They don't have any vertical asymptote.
Okay, so I don't know if I'll be able to factor that.
You don't have to factor it. You don't have to do anything. All right, 26. 26. Guys, shh. Don't forget I'm still recording. What about this one? First question today's homework says, is there a vertical asymptote? No, there's not a vertical asymptote on there. Are there points of discontinuity? Yes. Where are they at? -2 and +2. Now, there's a gap. There's a gap. So on this one, where like the last one, we had it wrote like this. This one would be -infinity. Do we include 2 or not? Hold on and I'll tell you, show you how you figure that out. Look at 2 and -2. Do we include them? No. So -2 is not included. Then it jumps to +2 to infinity. See the difference? Why? It'll go to the vertical asymptote. It will not be a gap like that. Gaps are not vertical asymptotes. So like if you have a vertical asymptote, it'll literally come right by it. Where this graph was a big, huge gap that's not, they would be right next to it. No vertical asymptote, 26. All right, 28. Let's try this one. What about this one? You meant zoom in, didn't you? Hold on. Didn't really help you, right? So on the last one, you're looking at that x squared, whatever, you saw the gap. Did you see what your table was? It said error, 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 and then it had the other numbers. Check this one out. Do you see any more numbers? So this is not a gap. What is this? It is the vertical asymptote. So what's the difference? What's the difference? If you have to, put your table of values in. So if you're a little bit confused, go to your tables of values and see what happens. Where would it be? Nope. -3. -3. Yeah. Do what?
We would know it was just a gap or discontinuity if it started that.
Yeah.
Okay.
Yeah. Okay. What's your next one? Tan pi x. Yeah. Yeah. Yeah, so you can't just write a number because there's multiple vertical asymptotes. We got to figure out where they're at. Where do they look like they are right now? Remember, I'm zoomed in, so you're seeing 1, 2, whatever. Where's that look like they're at? Are they, your vertical asymptotes are not, that's 0 right there. This is 1. So where does it look like they're at? Not everywhere. In between 0 and 1, right? In between 1 and 2. What is in between 0 and 1? 1/2. So it's every integer plus a half. N plus 1/2. No pi. No pi. Just n plus 1/2.
Vertical asymptote at n plus 1.
Yes. 1/2. Because they're at half. So 0 plus 1/2 would mean it was at 1/2. 1 plus 1/2 would mean it's at 1.5. So everything that you're seeing. All right. This tan theta over theta, check that one out. So y equals tan x over x. This one's really crappy. So it's not really, it's not really in the middle. What you need to remember is how to graph these. And I know that you probably don't, and we'll go over it. So I definitely wanted to go over this one with you. Let's change our window. Negative pi over 2. Maybe we can see them now. So every line now is pi over 2. So we definitely know everything's happening at some kind of pi over 2, right? So here's how you're going to write this one. I'm trying not to use all my sticky notes. Pi over 2 plus n pi.
Now, what if they're on the test and just write pi?
then you only gave me one. There's multiple. So this gets the multiple. So this would be pi over 2. And then if you add 1, that would be 3 pi over 2. You see what I'm saying? So this is what's complicated. So if you're getting that it's pi over 2, you just got to figure out how to get the rest of them. All right. Are y'all done? I mean, okay. Look at 34.
Oh, let's look at 34.
Where's your vertical asymptote?
-1.
-1. Is it removable or non-removable? If we factor the top, can we mark out the bottom? No, we're not going to use a factor of 1. So this one is non-removable at -1. Non-removable at -1. Yes, ma'am. Both are non-removable. 38 through 52. 38 through 52. Your question will probably be on 46. Watch 42, you have to factor it. Watch 42, you have to factor it. 46 is weird, and 54, you will probably have questions on. Got it? I starred those, but there you go. The rest of it, you just make sure you have your calculator and graph it. That's all you need. Graph it. We'll go over it. Yesterday's homework, you might want to go back and look at it. You may understand it a little bit better today. And then we'll go over it on Tuesday. So I'll ask questions about 2-4 and 2-5 on Tuesday. Thanks, guys. Sorry I took your whole period.